Okay, in this section we're going to talk about binomial probability distribution. The idea here is that this is an example of a discrete probability distribution. Remember, discrete probability distributions only take on whole number values, 0, 1, 2, 3, and so forth, and then a probability is associated with each one of those values that the random variable can attain. So in this case, the binomial probability can only be either a success or a failure because of the prefix bi. Binomial means either you win or you lose. So the previous examples that we looked at, some of them for the expected value, for instance, were binomial examples. So we're going to take a look at binomial probability distributions and the proverb associated with this. Let another praise you and not your own mouth, a stranger and not your own lips. Leave the bragging to your friends and fans. And I really hope that you get this in this section, that you understand everything, but remember that just stay humble. Stay humble in all things. Leave the bragging to your fans and your friends. That's the best way to go. So here's random variables, a little picture to help you guys. Random variables can be discrete, can be continuous. If they are discrete, then the probability distribution will be like this. It'll take on only certain values, not the values in between. If it's continuous random variable, which we'll talk more about in chapter 6, you can take all of the different values in between on a certain interval, and all of the values can be attained. Okay? Here's another example. Probability of distribution of a binomial distribution, can only take values that are whole number values. That's why you have these columns. And in a standard normal, we'll take a look at in the next chapter, you have continuous random variable, which can take on all of these values here. Not just -1, but -0.95 and so forth. Okay? So that's the difference between a discrete and continuous probability distribution using a graph. On the one hand, binomial distribution, being a discrete probability distribution, can only take only whole numbers. And on the other hand, a standard normal, being a continuous probability distribution, can take on any possible value, even numbers between whole numbers or between integers. Now there's a definition for a binomial distribution. Probability distribution that is binomial has 4 characteristics. You need to remember these. This will be on the test. The binomial probability distribution results from the procedure that meets the following requirements. The first thing is, the procedure has a finite number of trials. A finite number of trials means you can keep going a long time, but at some point you're going to have to stop, right? Second criteria is the trials must be independent. They must be independent. One cannot influence the probability of the next trial. No conditional probability here. Successes on every trial have to have the same probability, right? You can't have the probability of success on first trial be a certain amount, and on the second trial the probability of success is different. The successes and the failures, therefore, on each consecutive trial have to be the same. Each trial can have only 2 outcomes, and that goes along with the prefix bi, 2 outcomes. You win or lose, green or not green, red or not red. Those are different ways of stating 2 things. And so I have a way for you guys to remember it. I don't know if this helps or not. FIST, F-I-S-T, finite amount of trials, independent trials, successes have the same probability every trial, and 2 outcomes. I hope this is relatively easy for you to remember. I will ask this one way or another on the test about the definition or the characteristics of a binomial distribution, and the acronym here is FIST, F-I-S-T, finite amount of trials, independent trials, successes have the same probability every trial, and then 2 outcomes. Okay, let's talk about examples and see if we can spot these to be binomial or not binomial. Here's the first example. In a drug trial, 800 subjects are treated with Lipitor. Doctors record a yes if the subject gets a headache within 24 hours and no if they don't. Well, let's go through it. F, finite amount of trials. Is there a finite amount of trials? Yes, there's 800 subjects, right? I stands for, are the trials independent? Yes, we would have to assume independence, because if you think about this, if 2 people are sitting in the same room and one is asked, do you have a headache? And he or she says yes, then most likely, or maybe, the other person would be influenced in a certain way to say yes or no based on what the first person reacted, however the first person reacted. So we're going to have to assume independence. S stands for is the success have the same probability every trial? And yes, that's the case because every single person is given the same Lipitor, the same amount of the drug. And so the probability of a success should be the same every single trial. And then T stands for if we have two trials, or two outcomes, excuse me. Yes, and we do have two outcomes because you have yes or no. Do you have a headache or do you not have a headache? And notice that there's some more examples here. Heads or tails, boy or girl, yes or no. Defective, not defective, green and not green are all examples of ways you can ask and use the binomial probability distribution in your calculations. So some more examples. The first one says, give 800 subjects a dose of Lipitor and ask them how they feel. If this is not a binomial distribution, which one does it violate? F, finite amount, yes, it's good. Independent, yes, they're independent trials. S is the probability of a success on every single trial the same? Yes, the same. They're given the same amount of dosage. That's assumed. The T, is there only two outcomes? Well, no. How they feel, I feel bad, I feel sad, I feel happy. There's a lot of different outcomes that they can report back. That breaks apart this example, and that therefore this is not a binomial distribution. Treating 152 couples with a fertility treatment and recording whether they have a boy or a girl. Just go through the FIST acronym. F, finite amount. Independent? Yes, they're independent. Successes are the same? Yes, girl or boy, 50-50 chance. And then are there only two outcomes? Yes, girl or boy. Okay? Third one, in one city, asking people if they are registered Democrat or not. F, in one city, is there a finite amount of people? Looks like there might not be a finite amount of people. And if you actually went through this, think about this, people moving in, moving out, you might be there for a while, for a long time, because you could not have surveyed everybody. So there's not a finite amount of people necessarily in a particular city. Independent, yes, you'd have to assume independent, talk to them one at a time. S, successes happen with the same probability. You would assume, yes, that's true. There is a certain percent Democrats, certain percent Republicans, certain percent independents, and so forth in a particular city, and therefore that probability of meeting one or the other, it would be the same every single time. And the last thing, are there only two outcomes? Yes, it says Democrat or not. So all of the other parties are put into this not, and then the Democrat question would be put into the other. So the only problem I see with this one would be in one city, you don't know how many people there are necessarily. So there's an indefinite, undisclosed amount of people that are being surveyed. That means that is not a binomial distribution. Okay, variables. There is a formula for this binomial probability distribution. N stands for the finite number of trials. X stands for the specific number of successes in the N trials. P stands for the probability of a success. Q stands for the probability of a failure. And note that because there's only two outcomes, 100% of the probability is distributed to these two outcomes. And therefore, the relationship between Q and P is that 1 minus P is equal to Q, or you can do the other way around, 1 minus Q is equal to P. So you can figure out what is the probability of a failure if you are given the probability of a success, or you can figure out the probability of a success if you're given the probability of a failure. P of X, probability of getting exactly X successes among N trials. Okay, I'm going to show you how to evaluate the probability for a binomial probability distribution, 3 methods. The first being the formula, the second being the table, and the third being your calculator. Obviously, you're going to end up using your calculator eventually, but I want to make sure you're aware that there are 3 ways that you can go about this answering questions. Here's the first one, method 1, binomial probability formula. Now, if you notice, it's relatively complex, but you've seen all of these elements. You've seen this n factorial divided by n minus x factorial times x factorial p to the x, q to the n minus x. Let's break this formula down a little bit because I really want to play, the instructor who goes down the middle. I don't want to give you a formula you don't understand. I don't want you just to learn how to do this on a calculator. I want you to do both. You should be able to recognize the formula, know what it stands for, and use it. You should also know how to do this on a calculator. I want to make sure you know how to do both. So n stands for the number of trials. X stands for the number of successes in these n trials. P stands for the probability of a success. Again, X stands for the number of successes you expect. Q stands for the probability of a failure. And n minus x is the number of failures that you expect, right? So, and then for calculators, you can just use the NCR key under the probability menu wherever r equals x, right? Wherever you see an x, that would be the r value. So that's the formula for it. Let me break this down a little bit more so you understand the pieces. The result of this p of x should be some number that's going to be less than 1, right? This portion right here, NCR, or NCX, if you will, if you're just using the x variable, stands for the number of outcomes with exactly x successes among n trials. So, what are the number of outcomes with x successes among n trials? Maybe stop and think about that. That's what this portion of the formula says. The number of outcomes with exactly x successes among the n trials. This portion of the formula has to do with the probability. So number of times the probability. Number of times the probability. And this portion stands for the probability of x successes among n trials for any one particular order. I know that's a mouthful. Probability of x successes among n trials for any one particular order. So, you can have number of successes. The number of successes can be in a certain order among the n trials. And so for any one particular order, this is the probability of getting x successes. I hope that's a little bit more helpful. Maybe rewind the video or read through these little notes that I have to make sure you understand the formula. Okay, I should be able to ask you about any part of the formula, and you should know what it stands for. What does the P stand for? What does the X? What does the Q stand for? I might be able to. You will most likely see multiple choice questions pertaining to this formula. Okay, let's actually put it into action and use the formula. Find the probability of getting exactly 2 correct responses among 5 different requests from directory assistants. Assume in general they are correct 80% of the time. Now, some of you might not know what directory assistance is. Basically, it's a service where you call in and like in a hotel or something, or in a phone company, and you ask for help finding a burger place, finding a pasta place, finding something else in a particular city. And this question says that you want to find out what is the probability that you get exactly 2 correct answers from directory assistants among 5 different requests, right? You call 5 times. What's the probability that 2 of those answers will be correct? And there, it actually tells you, assume that in general, they are correct 80% of the time, right? So 80% of the time means they're going to be, most of the time, they're going to be correct. The binomial setup would be this. The number of trials would be 5, and I always suggest for these binomial distributions, when you notice that there are 2 outcomes, they're right or wrong information, in this case, you write down nxpq, or in any order you want. What's the number of trials? 5. What's the number of successes you're looking for? Exactly 2. What's the probability of 1 success? It's 0.8 in this case. Probability of a failure is 1 minus that, which is 0.2. And then using the probability formula for the binomial probability, you would have 5 choose 2, right? Nx, 5 and 2, times 0.8 squared. The squared is the number of expected successes. And then 0.2 cubed, the 3 is 5 minus 2, the rest of it, right? So So you should always expect that these two exponents, the 2 and the 3 in this case, will always add up to the number of trials you have. And if you go through that, you get 0.0512. Well, that's actually a relatively small probability. Does this make sense? That you have a small probability that among 5 calls, you get 2 of them to be correct. Yes, that does make sense because think about this. It says that most of the time, 80% of the time, they are correct. So it's very unlikely that you only get 2 correct answers among 5. Most likely, you will get 4 correct answers among 5. That is a higher probability because most of the time they are correct. That's why this probability is low. 2 of 5 correct answers from directory assistance is a smaller probability than if you were going to do 4 out of 5, granted that you have this probability of getting them correct, right? You get a correct answer out of them 80% of the time. I hope that helps going through the formula. Again, try putting these into your calculator, into your formula and then calculating them by hand. Of course, you can use the calculator, but you're not using the functions in the calculator that I'll expose you guys to here in just a little bit, okay? So binomial probability distribution, you recognize that there's only 2 outcomes. There's a finite amount of trials. They're all independent trials. Each phone call is independent, and you have only 2 outcomes, and the success is the same for every single call. 80% of the time they're correct. Okay, so here's another example. Toss a coin 3 times. Let x be the number of heads, and find the probability that you get exactly 2 heads, probability that you get at most 2 heads. Well, be very careful again. This is a binomial experiment, so you need to know 4 things: p, q, n, and x, or n in any order you want. N is the number of trials, so you're going to toss a coin 3 times. That's 3. Probability of success is 0.5. Probability of failure is 0.5, 50-50 chance. And then you're asked for, what's the probability that among 3 flips you'll get 2 heads? What's the probability that you get at most 2? Now be very careful about this. At most 2, think about this, means 2 or less. At most 2. The most you can get is 2. Well, if the most you can get is 2, then you can get less than 2, which is 1 or 0. And that's what this means. And so you can go about this a couple of ways. Let me actually write out the formulas for you. So the first thing is probably that you have x is equal to 2 heads. So you have 3 choose 2 times the probability of a success is 0.5, and you're going to get 2 heads. The probability of a failure is 0.5, and you're going to get 1 head, or 1 tail, because that would be considered the failure, right? You're interested in 2 heads out of 3 tosses. Notice my exponents add up to 3. That's the number of trials. And then I'd calculate this. I can put this into my calculator, of course, or I can do this by hand. I can say n factorial, which is 3 in this case, 3 factorial divided by 3 minus 2 factorial times 2 factorial times 0.5 squared is 0.25 times 0.5 to the first power is 0.5. You have 3, 2, 1 in the numerator of our fraction. 3 minus 2 is 1, so 1 factorial times 2 factorial. 0.25 times 0.5 is 0.125, so 0.125. You see, we don't even need a calculator, we can do this by hand. And then 2 factorial, we have 3 times 2 times 1 divided by 1, 2 times 1, 3 times 2 times 1, there we go. And so the 1s and the 2s cancel here, and you get 3 times 0.125, should write like that maybe, 0.125. You have 3 times 0.125 is equal to 0.375. So that's the probability that you get 2 heads out of 3 coin tosses. And that's that probability. Okay, that's part A. Part B says at most 2. What's the probability that you get at most 2? And at most 2 would be written as x is less than or equal to 2. But that just means the same thing as probability that you get x is equal to 0, 0 heads, plus the probability that you get one head plus the probability that you get two heads. So I actually have to do this calculation here at least two more times, or a total of three times, but we've already done this one right here, right? And then add up all those probabilities. So I'm going to just write out the formula, and you would be able to fill in the values. So we have x equals 0. Among three coin tosses, 0 of them are heads. 0.5 to the 0 power, 0.5 to the third power, 3 failures, 3 tails, and 0 heads, plus 3 choose 1 heads out of 3 coin tosses, times 0.5 to the first, times 0.5 to the second, plus what we just did above, x equals 2, we have 3 choose 2 times 0.5 to the second times 0.5 to the first power. Okay, and I calculate each one of those, and this would be my total probability. Now, question would be, maybe check your intuition. Guess first, and then go through the calculation and see if your intuition is good. Is it going to be greater than 0.5? Is it going to be less than 0.5? Think about it. Okay, so hopefully that helps you understand how to use the formula, not in just x equals situations, but x less than or equal to 2 situations. Okay. Here's another one. Find the probability of getting exactly 3 heads when you flip 5 quarters. Write out the formula and give the probability. So 5 trials, we have probability that you get exactly 3, right? It says exactly 3. 5, choose 3 times, flipping a coin, 0.5 to the third times 0.5 to the second, the exponents add to 5, the total number of trials, and then we would calculate this and get the probability. Okay, I'll let you practice that one. In poker, the probability of getting dealt a full house is 0.0014. A full house is 3 of a kind in a pair in the same hand. What is the probability that you get 1 full house in 7 hands? Okay, 1 full house in 7 hands. Well, let's do this like a full-blown example where we actually recognize that we can get the full house or not get the full house, right? This is a binomial experiment. And so we have n, p, q, and x to find. So n, the number of trials is 7. The probability of winning is 0.0014. 1 minus 0.0014, which is, so 1 minus 0.0014 is 0.9986, and then the number of successes is 1 full house among 7 trials. I have all my values, and I can find out what's the probability of getting exactly 1 full house out of 7 hands. So x equals 1. That would equal 7 choose 1 times the probability of a success, 0.0014 raised to the first power, times the probability of a failure, 0.9986 raised to the 6th power. And that's my setup for the formula. And then I'd calculate that and get what the probability is, either by calculator or by hand. Again, I can just do one more step and leave it up to you to put this into your calculator. 7 factorial divided by 7 minus 1 factorial times 1 factorial times 0.0014 to the first times 0.9986 to the 6th, and then you can calculate it from there. Okay? Hopefully this binomial probability formula is sticking in your head a little bit better, so you can use it when you recognize a binomial experiment. Okay, in the next video I'm going to show you method 2, how to use the website, well actually the table, and the table is available on the website under tables, probability distribution tables. And then I'll also show you guys the calculator as well.